Well, I think it's time to start. Hopefully, we get some others in class, but I appreciate Salhan Raja for your work ethic and making it in today. Today's class, we're going to be going through section 3.2. And if we have additional time, we'll take a look at section 3.3 as well. I think there's a good chance we'll take a look at that one, but we won't try to rush it. So we'll begin through 3.2 and work as normal. But any questions at all, folks, before we get started? Okay, well, here's the next thing we're going to get into in the wild world of determinants. In section 3.1, determinants look like it's something that's always going to be pretty nasty unless you have lots of zeros. But in section 3.2, with the right properties of determinants, it's actually not too bad to do a large matrix as a determinant if you use the right strategy. So here's the strategy pretty much. Highlighted in yellow, the one that's used quite often, not as if the other two properties or the theorem below are useless, but this one is pretty major. It turns out with determinants, you can combine them with row operations. So if you take this row operation, add a multiple of one row to another to produce a brand new matrix B, you haven't changed the determinant at all. That's fantastic because we could go here, maybe do some row operations that cause zeros in this location, and then that would immediately free up for a decent cofactor expansion on this thing. Without row operations, doing this as a 3x3 could actually be a pretty long and tedious computation. And there's other great things we're going to take a look at. We'll use them on the matrices below. Over here, for example, it says, well, it's not as great as this one where there is no change on the determinant if you use that row operation. But if you ever do swap a row, you have to track a negative sign. And you can also factor out a value k or multiply a value k, but you have to keep track of that k value as well, whatever the constant might be. If you do something like this, multiply all rows of A by k, which is what that's indicating, then if A matrix is size n by n, you get k to the power of n times the determinant. So that's our property so far. Again, I think of this one as probably the major one in the list. So let's start off by doing that. We'll use row operations, cofactor expansion, to try to find the easiest method to run through this. And looking through these, yeah, eliminating the 4 and 6 should be pretty standard on this. Notice we're not using row equivalents. We would use this if we were matching up one matrix with another using row operations. But this thing right here is an ordinary number. It's a scalar. And so it's actually appropriate to use equality despite the fact we're using row operations on this thing. In fact, a row operation symbol for row equivalence wouldn't even make sense. So that's something that's a little bit weird about the notation for these things. But beyond that, it's not too bad to calculate. Let's carry in row 1 as 2, 1, 3. And that should be a bar, not a bracket. If we multiply by -2, add to the row below, we'll get 0, 0, -5. And already that's probably a good spot to stop right there. We have produced a bunch of zeros in one row, so cofactor expansion going this way now makes sense. So let's put in, say, 6, -3, 4. You could do a row operation there, but one hint with this kind of stuff is you don't necessarily want to do a whole bunch of row operations. You want to do just enough so that you have lots of zeros for an efficient cofactor expansion. If we try to row reduce this to, say, echelon form, or heaven forbid, row reduce echelon form, we're making the problem way worse, so you might as well just do the determinant over here. Well, for that cofactor expansion, the review on this is you have to keep track of the signs. So we'll start off as, if you like a sign chart, positive, negative, positive, and negative. So what I'm thinking of is, in this corner, the sign is positive. They alternate going this way. So I built out a little line that goes like this. Just to remind me that right here, we have to multiply by -1 for that coefficient. So it's going to be -5. Have a smaller matrix, probably a little bit appropriate. We'll delete that whole row, that whole column, and carry in 2, 1, 6, -3. At this stage, it's pretty much done. There's no real call to do any row operations inside this if it's a 2x2. We're just going to carry in 5, take the product of the main diagonal for a -6, minus 6 for the off diagonal. And let's see here, it's 5 times negative 12. And so this will turn into negative 60 altogether. So that's doing that determinant there pretty much as fast as possible. Again, without row operations, this one can get kind of messy to work through. Well, any questions, folks, on how that theorem worked for us up here? Okay, that's kind of nice in a way. Determinants can be a little bit sketchy to calculate, but we're pretty good at row operations. We've been doing a ton of them. And now let's try this one down below. Notice it almost looks like this matrix right here. It just has something that's been multiplied in row 1. What this theorem is saying is you can in fact just factor out a value. So over here, let's factor out to 10. We're only factoring out from one single row, so row 1. If we were factoring out a 10 from all 3 rows, it'd have to be a 10 to the power 3. So this will give us 2, 1, 3, 4, 2, 1, 6, negative 3, 4. And then that determinant is pretty much done since we've already calculated that one. It came out as negative 60. So it's 10 by negative 60 for a negative 600. That's 2 pretty nasty looking determinants done pretty quickly so far. Any questions at the moment?
I have a question over there. So is the 10 the factor for the row 1 or for the whole matrix?
Just for one single row. So just the row 1 there.
Mm-hmm. And
hard to highlight.
Multiplied by negative 60. So negative 60 is the for the whole matrix.
Yeah, exactly. That was for this portion right here, which resulted in that same matrix. Exactly. So it just came out as, by substitution, that negative 60.
Does it apply for the second and third row too, or?
Are you saying this factoring out of a 10?
Yeah, if you can factor from the row 2 and row 3, can we do the same?
Yes, you could factor out a 10 from all 3 rows if you wanted to. You'd have 10 to the power 3 if you factored from all rows. And then all the stuff right here, you just divide by 10. Is that what you were asking about, factoring from all rows?
Yeah. Yep, yes. Gotcha.
Awesome.
Thank you.
You betcha. Other questions so far? Okay, well, here's one more to go. This one's a little bit odd since it's just, we could try to do a cofactor expansion on it, but if you could get it in the right shape, if you got it in a triangular form or a diagonal form, the determinant of this thing would be immediate. So what we want to do is this property. If we just interchange the right rows, we can put it into a diagonal form, and then the determinant would just be product of the main diagonal. But the trouble with this portion right here is, I think of part B as the trickiest theorem. You have to count every single row swap that you make. So let's see if we can do that. Bring this a little bit higher up. If we're going to do some row swaps, we would say that row 2 ought to be the very first row. So it'd be 4, 0, 0, 0 to start. The top row right here, we ought to make it the last row. So down below it's 0, 0, 0, 3. Then after that, let's see what we have. We should move these 2 rows up. So this one goes 0, negative 1, 0, 0, and finally 0, 0, 2, 0. So we put it into its nice format, but now we have to track the contribution from that negative right there. Let me see if I can fit in some little space. It'll be negative 1 to some power. We have to find that power, actually. It's all going to be the number of row swaps we made. Anyone see how many row swaps that actually would be to get to that stage? Let's see. I don't think it's 4, but it's really hard to track, honestly. One way you can think about it is we were trying to get this row to the very top, right? And that one to the very bottom. And so we did a swap this way. That was swap 1, right? But then we swapped again from here to here. We were swapping the next 2 rows. to get this one to the very, very bottom. And then we swapped a third time to get that to the very ground bottom right there. It looks like 3 swaps altogether, but it's super hard to visualize. Let me see if we can visualize it this way. On swap 1, you would have 4, 0, 0, 3. Oh, that's also a 0. And 0, 0, 0, 3, 0, that's kind of weird, 0, -1, 0, 0, 0, 0, 2, 0. So that's swap 1. But then you want to swap these two once again. You swap those two, it became this 0, -1, 0, 0. This is 2 swaps at this point, and 0, 0, 0, 3. So let's count them, 2 swaps. Does that make sense at the moment? Then we'll do it again. We need to bring that one to the very bottom. But at this stage, it looks like it really could be thought of as 3 swaps altogether that we had to really do. So up here, this would be raised to the power of 3. But all it boils down to is we're multiplying by a -1. So it's all about, was it an even amount of swaps or an odd amount of swaps altogether? Does that make sense to track those through? Awesome. So with that, all that out of the way, the determinant is pretty much done. We have a triangular matrix. This value is going to come out as a -1. Then just take the product of the meg diagonal. It'll be 4, -1, 2, and 3. Multiplying all those together, it looks like we've got a value of 24 altogether. And we did it, folks. That's a not terrible determinant to get through, but the trickiness is how many row swaps to get to that right spot. So that was the use of part B of that theorem. Any questions at the moment? Okay. Well, for the next problems, I did want to insert an additional exercise. And those for the homework that I assigned. There's one problem that we really didn't get to, which is dealing with the 4x4 matrix. So let's do kind of an impromptu one just to support the homework. We're going to use this theorem right here to help us out. We'll do it right in front of this one right here. Let's just call this an additional example. And what we'll do is compute this thing. It's going to be a larger determinant. This one is size 4x4. You'll see these in the homework as well. And this one goes 2, 4, 6, -6. Column 2 is 5, 7, -2, 7. Column 3 goes 4, 6, -4, 7. And finally, column 4 is 1, 2, 0, 0. So that's our problem to get through. And this one could be a legitimate exam kind of problem as well. If you see this as an exam problem, a 4x4 determinant, it's almost an expectation that we're going to use this theorem somehow. And surely you could get through it doing a cofactor expansion down column 4, but now you have to do 2 3x3 matrices. It's just not worth it if you can shorten that up. So we'll do exactly that. Let's see if we can eliminate, how about that 2 right there, and see what happens. So we'll use part B. That copy didn't work. I think the lettering changed the way I copied and pasted in. That's meant to be part A right there. Really weird. Let's use part A officially. I'll carry row 1 in as 2, 5, 4, 1. Multiply row 1 by, let's do -2 to eliminate that entry. And we'll get a 0 here. That's nice. -3 from here. We're multiplying by -2, so that's -8 plus 6 for a -2. And on this one, by design, we get a 0. We could try to go for more zeros, but again, it's usually better just carrying what you have and not go too crazy with row operations. So I'll carry the last 2 rows just as they are. 6, -2, -4, 0, -6, 7, 7, 0. And finally, we'll do a cofactor expansion going down that way. If the sign chart helps, you can write out positive, negative, which tells us we'll start by multiplying -1 right here. Any questions at the moment, folks, with that setup? Okay, so we're reducing a 4x4 determinant to a 3x3. We just have to multiply by the negative here on that value 1.
I do have a quick question.
Yeah, go ahead.
So the reasoning for doing this is just to increase the number of zeros that we have in the matrix to make the determinant easier to get, right?
Yeah, absolutely. That's kind of the whole gist of this kind of thing. If this as an exam question without using row operations would make it a really nasty kind of problem. So it's really just for the sake of fast computation by hand.
Thank you.
Other questions at the moment? Okay, and with what we have so far, we're going to eliminate that entire column, this entire row. So we'll get 0, -3, -2. And I did not format that well. Let me try again. 0, -3, -2. That looks a little bit better. Then 6, -2, -4. Finally, -6, 7, 7. Then looking at this one, you could settle for just doing this determinant as is, or take row 2, add it to row 3, and you have even more zeros. Always worth it if you can cut down the computations and reduce the number of determinants. So let's say that this is equal to negative. Another 3x3 will go 0, -3, -2. And depending on how you do it, I think I'll just keep this row as is, 6, -2, -4, but then add it to the row below to get 0, 5, 3. Does that look right to folks so far? Okay, well, we now have a pretty good cofactor expansion going down column 1. The sign chart would be positive and then negative. So we'll have a negative on this quantity, as well as that extra negative. And so next step will be negative. Then this 6 with a sign of negative as well. So -6. Now we boiled it down to a single 2x2 determinant. That's definitely easier to calculate for sure. Eliminate that row, that column, and we have -3, -2, 5, and 3. At this stage, it's pretty much all done. We just have to crank out the last bit. We have +6. Main diagonal gives us a -9. The off diagonal will give us, well, -10, but we flip the sign, making it a +10. Or you can think of it like this for safety. There's always an extra negative there. And then the product came out as a -10. So this is glorified 10 plus -9 for a 1. The whole thing turns into a determinant of 6 altogether. Well, again, watch out for problems like this in the homework. You're not meant to work too hard. These are meant to get by pretty quickly. And if you see stuff like this on the exam, it's, again, almost a complete expectation you're using this theorem in some way. Any questions, folks, on completing this one? Okay, well, that's kind of the main work we're doing in this section is just getting used to the available properties. This is probably the biggest one. But there's other good properties as well. Like, for example, this one. It's really a callback from the vertible matrix theorem. It's the last statement in the vertible matrix theorem. But our author decided might as well just highlight it here and now. Just to be specific, a matrix A is invertible if and only if the determinant is not 0. But whenever you read those kinds of statements, really you'd want to turn to probably section 2.3, because this is the entire theorem. We often need the whole thing. And what that gave us was relating A to part M. But example 2 is a little bit different. It says, well, we have 3 different vectors, and they're asking us the question, is the span of those vectors equal to R3? You have a lot of different ways to answer that. You could use theorem 4 from chapter 1, for example. You could put all of these into a matrix, row reduced to echelon form, and if there's a pivot in every row, you'd say, yes, the columns here would span R3. But this is giving us just a different kind of tool. We can instead say, let A equal V1, V2, V3, then just calculate the determinant of A. So that's a nice theorem because now you have options. You don't have to row reduce on everything. If you suspect the determinant's faster, then it's a decent one to go through. Let's take a look for us. I'm not too sure if this is faster than row reduction, but it's good practice regardless. Determinant of A is, we indicated A goes V1, V2, V3, so it'll be 1, 5, 0, 0, 3, negative 2, 1, 8, negative 2. And we could do this determinant as normal, but honestly, if there's a tool that can make this faster, we might as well use it. Let's try to eliminate that entry right there. So next determinant will be equal to 1, 0, 1. Multiply row 1 by negative 5, adding below will give us 0, 3, and 3. Copying down, we have 0, negative 2, negative 2. And we're pretty much done at that stage. Now, these rows are kind of interesting in a way. 3, 3, and negative 2, negative 2. That means row 1 is a multiple, or row 2, rather, is a multiple of row 3 in a certain sense. It looks like this determinant should come out as 0, but let's see what really happens. We'll go a cofactor expansion this way. In that corner, the first sign we had fixed to it is a positive, so we usually don't worry about the sign chart in this situation. I'll just put a 1 here to say we used it. We'll carry in this right corner, 3, 3, negative 2, negative 2. And watch as we do this determinant. This will be negative 6 going this way, minus negative 6 going this way. And that's a determinant of 0 just immediately at that stage. That's kind of nice, but it didn't answer our question. They asked us, is span V1, V2, V3 equal to R3? But what we can say is the matrix is not invertible. I'll abbreviate by saying A inverse does not exist. Lots of ways to say this. You can say A is singular, A is not invertible, or this would be my version I usually use. That takes us back to the invertible matrix theorem. If A is not an invertible matrix, we can now come down and say the columns of A do not span R3 in this case by part H of the invertible matrix theorem. Let's make that our conclusion. By part H of the invertible matrix theorem, the columns of A do not span R3. The question was, do these span R3 or not? But those form the actual matrix A, so it's okay to just conclude by saying columns of A at this point. Well, we did it, folks. We use the invertible matrix theorem, and kind of the reminder about example 2 is this thing is not going to go away. It's, in fact, just going to get longer as we go through linear algebra and pick up more and more definitions and results. So it's always a good thing to, I'd say, have it printed out to always available as you work linear algebra. Always think about those concepts and how they relate to each other. Well, any other questions or comments at the moment? Okay, let's take a look at what we're getting to next. Here are the other properties of determinants, and some of these are really quite nice. For example, if you need to calculate the determinant of a transposed matrix, it just falls back to the determinant of a matrix A itself. And that ought to make sense because, for an example, you can do a determinant on this one by doing a cofactor expansion down row 1. If you transposed it, it'd be a cofactor expansion down column 1. It's going to come out as the same exact way. Next property is massively important. It says if you take the determinant of A times B, and this is weird in mathematics, you get a factorization, determinant A times determinant B. It's, again, actually pretty weird to have a property that works in this nice way. Next one says, if you take the determinant of the inverse of A, you get 1 over determinant of A. Finally, the last theorem says, determinant of A to a power is written out this way. Determinant of A to power n in that way. Well, how do these all go together? This is the really, really hard one to prove. Our author, I believe, doesn't even make an attempt on it. I'd have to double check that, but I believe he just leaves that to an appendix or something like this. But once you have this property down, the next two theorems follow directly from it. These are not theorems our author decided to state, so I just stated myself. I felt like they were important enough to actually write down. And let's verify maybe that one. I think that's the funner one to try out. So we'll do a derivation for this. But any derivation we do is really more about just a quick review of information we ought to be familiar with. It said A is invertible, so in our derivation, we can take A times A inverse, and we know that that product always gives you the identity matrix right away. Next thing we're going to do is, let's use this theorem right away. You have a matrix times another matrix, so that qualifies for the determinant of a product right here. You would get determinant A times A inverse equals determinant of I. And by the way, this is a real exam question sometimes. It could be a concept question. It can be tricky, but if you think your way through it, it shouldn't be too bad. Anyone see what determinant of I ought to be?
I think it's going to be 1.
Exactly. It's a 1 because the identity matrix, if it's a, let's put down just a 3 by 3, goes this way. So you're just taking the product of the main diagonal. I mean, that can be kind of confusing on an exam. So this is actually a pretty decent property already on its own to think about. Okay, so now, thanks to that property, the right-hand side is just a value of 1. That's nice. And thanks to this property, we can do a factorization right here. Again, that is pretty weird, but it's allowed now. It would be determinant of A times determinant of A inverse. Let me see if I can fit that in a little bit better. Equals 1. So there we have it. We haven't proved this yet. And in fact, it looks like there could be some problems in proving that. For example, I can't just necessarily divide by the determinant of A inverse. We need to know something about that. But this is the key. If they told us A is invertible, that implies determinant A inverse is not 0. That was the theorem that we just used from the invertible matrix theorem. And that says by division by this, it really is allowed. We're home free on that. One thing to keep in mind as well as an additional concept is if you had A times B equals, say, an identity matrix, you cannot divide by B at all. It doesn't work like that. You'd have to multiply by B inverse as the closest analogy. And B might not even be invertible. That could be impossible. So why are we allowed to divide here? It's because each of these things, they're not even matrices. Those are ordinary real numbers. Think like 3 and 5, and you can divide using normal algebra for these things, as long as there's a determinant function right in front of it. Otherwise, they're full-on matrices, and algebra suddenly breaks down and works different. So all this to say, determinant of A inverse, I'm going to keep this one right here and divide by that determinant of A. 1 over determinant of A. And reading that, that is correct, but I think the concept I really want to say is determinant of A itself is not 0. So I could do that actual division. Kind of got a little sidetracked with that one. Any questions, folks, on getting to that stage of the derivation? Okay, another thing you could do with this is you could say determinant of A inverse equals, then take this right here and just use ordinary exponentiation notation. Think of determinant of A as the base. If you throw it into the numerator as determinant of A, it would require a power of -1. And so this is a cool way to view what the determinant function is actually doing with these properties. A power right here can emerge as a power over here on the outside. And that's very unusual for a function. So determinant function is really special like that. In fact, that's what's happening up here. A to the power of n just means a times a times a, n times. And that nth power emerges right there as well. So that's a nice key property of determinants. All of them come from that statement there. So that's our properties of determinants. Any questions at the moment with them? Okay, going forward, here's where we'll actually use them. They tell us for this matrix A, calculate its determinant, and then all these additional things we want to take a look at. Think of these kinds of problems as you're really just practicing these above properties and other properties we had when we get through all of these. First thing we want is fast computation for the determinant of A. It'll go determinant A equals, and it can be very, very fast. Let's leave row 1 right where it is, 1, 5, -4. Then we can take row 1, add it to row 2 to get 0, 1, 1. Double row 1, add it to row 3 to get 0, 2, -1. All those operations leave the determinant completely unchanged. And now we'll just do a cofactor expansion going down column 1. This will boil down to 1 times 1, 1, 2, -1. So this determinant will be done really fast. Main diagonal will give us a -1, minus the off diagonal of -2. Settles us down to -3 on that total determinant. So that was computing determinant of A. Now we'll go down the line for all these other things as well. Any questions so far? Okay, let's try out this one next. It says determinant A squared. The nice property here is you could just take that whole thing and go determinant of A. Not sure how I'm picking that thing up, to power 2. And that's this property right here. Again, it's an unnamed theorem in the text, so it's a good one to kind of highlight or maybe write down when you're about to do a homework problem, since it's one that is really very powerful, I'd say. When we get down to here, we're just going to put in the value of determinant of A. It was a -3 squared, so we get 9 altogether. Throwing that thing right in there. So we did it, folks. That's the first one. All we're going to take a look at is some iterations of these. Next one says determinant A inverse. Property on this one gives us 1 over determinant of A. So we'll get 1 over -3 altogether. To me, that always kind of looks funny. I usually write this fraction in as a -1/3. This looks a little bit more normal, but you could leave it like that if you wanted to. So that's our property for inverses. Next one is for transposition. So if we transpose this entire matrix, we want to know what the determinant of that one should come out as. So determinant A transpose. Again, it's not so bad. That's this first theorem number 5 here. Just the same as determinant of A, which gives us -3. Well, any questions, folks, with those 4 computations at the moment? Okay, the next one I have is actually a little bit nasty in a certain sense. I probably should have put a theorem here because the theorem we need for determinant twice A is not actually listed anywhere here. What we want is that one. Okay, let's just plug that in or make it available right here as we go to work this next part. So we want to do determinant of twice A. So this value here, we know determinant of A is -3. But when we say twice A, it means we're multiplying every single row of A by that value of 2. We're essentially doing this right here. This can be kind of tricky to miss, in my opinion. It turns out it comes as a k to a power of n multiplied by the old determinant And the value of n comes from the size of the matrix we're working on. This one is size 3 by 3. So because it's of size 3 by 3, and we're rescaling every row by 2, this one comes out as 2 to the power 3. That just doesn't look official. Let's put it in this way. 2 to the power 3 times determinant of A. So to me, this one is actually a pretty tricky one to think about because of the way it's using this theorem. Another one the author didn't think to actually name, so that's why there's no number on this one. But once we see the trick, it's just going to turn into a -8, or excuse me, an 8 times -3, resulting in -24 for that determinant. Well, we did it, folks. That's the tour of properties of determinants with these things. Any questions at the moment? Okay, definitely riveting stuff. There's problems like these in the homework. I think this is one where it said in the homework, problem number 45 is worth 10 points. So we're doing those kinds of problems that has multiple parts altogether. And because it can be tricky, and it's also probably definitely an exam problem to do one of these or several of these, let's practice it again with this context. So I've carried down the same properties as before, theorems 5, 6, and the unnamed ones. All we know about matrices A and B is that they're both of size 3 by 3. That will be important later. So let's just circle it as a reminder. We know the value of the determinant of A is 4, and determinant B is 5 on this one. So just more practice working with the properties, and they're really not too bad. If you see determinant A times B, in an exam setting, if you just took 4 by 5 and wrote down 20, that's completely fine. I'd say you know the property, and you're just moving through the problem really quickly. But for the sake of the homework, when you're learning these properties, it's actually a pretty good advantage to write out this way. Determinant A, and you don't have to color code, but I'm going to do that for the sake of the notes. Determinant A times determinant B. If you write down the properties each and every time you're about to use them in the homework, that is always a really, really great way to absorb this kind of stuff, involving more of your senses as you work through it. So now determinant of A came out as a 4. Determinant B is a 5. And so there it is. We get a 20 altogether on that thing. So that one's not too bad because we're using this property in a direct way. It's clear we're just multiplying. But this one is now the tricky one of the set, determinant of 3 times A. It'll go determinant 3A equals, it will be 3 to this power that we indicated up here. So it has to be now to power 3, multiplied by determinant A. At this stage, we're pretty much done. 3 to the power 3 comes out as a 27. Determinant of A is a 4, and good reminder for a calculator on the exam, since they are allowed. I try to keep the numbers more manageable, but this would be a good case to have one. That's something like 108 maybe. Let me know if my numbers are weird. And that's 2 down so far. Any questions at the moment, folks, with these? Okay, so this one is a little bit nasty, but if you see how this one goes, the next one down the line is really not too different in a certain sense. Calculating determinant 2AB. It's much like calculating this determinant right here. The major trickery is that scalar of 2 is rescaling the entire product A times B, so it should be raised 2 to the power 3. And let me do that differently. Then we have to multiply by, let's see here, determinant of A, multiply again by determinant of B. And we're well on our way at that stage. Really what we could have done to save some time is, we already knew determinant of AB was 20, so it's just 2 to the power of 3 times 20 altogether. But looks like I worked it from scratch, forgetting we already did determinant A times B, so we'll keep it in this line. 2 to the power 3 will give us the 8. Determinant of A is a 4. Determinant of B is a 5. So now it's 20 times 8, giving us 160 altogether. So that's determinant twice AB. Again, could have done that one a little bit shorter, but writing it out like this is practicing the property, so who cares? I think that's worthy. Last one is determinant of A inverse times B. And for that one, we have to start combining properties. We need to use this right here to break it up. Then we'll use this right here to handle the determinant of the inverse. And you could just put them both together if you'd like. So with theorem 6 and the unnamed theorem together, you could take this determinant A inverse B and write out this way. Determinant of B stays exactly where it is. And by the theorem under theorem 6, determinant of A should go down here in the denominator. So we'll just throw it there right now. So here's determinant of A. And now we're pretty much done. We'll grab the value for determinant of B, which is 5. Divide by determinant of A, which is 4. And it's done at that stage. Well, any other questions, folks, on getting through these? Okay, they're honestly kind of weird problems because we're not doing a whole lot. We're just plugging in information, doing lots of substitutions. The whole purpose is just to get familiarity with the properties that we have on the table. Well, we got through the major meat of this section. There's one additional problem I wanted to take a look at just for the sake of extra practice with weird terminology and linear algebra. Linear algebra has a good amount of terminology because there's a lot of different kind of matrices that show up routinely in different processes. One of them is skew symmetry. By definition, a matrix is skew symmetric if you transpose it and the result is -1 rescaling the original matrix. So that gives you something that is skew symmetric. The problem goes on to say, if you have an n by n skew symmetric matrix and n is odd, show that the columns of A are linearly dependent. This one is really kind of a vertible matrix theorem kind of question. So if you're thinking in these terms, we're trying to show which part. Columns of A are dependent. We're trying to show that this is false. So we need a way to get into this theorem. We don't have a matrix so we can determine if it's invertible or not directly, but we could use the determinant. This one down here is a pretty powerful statement. So let's take a look at how we're going to use the determinant. That's a good question as well. Let's see. We need to show the columns of A are linearly dependent. The only couple things we know about A is it's skew symmetric and n is odd. So let's start with that equation. By skew symmetry, A transposed is -A. So that gets us started. Again, our goal is linear dependence. I don't know anything about the matrix A. It's transposed or it rescaled by -1. So let's just try hitting it with the determinant and hope for the best. It'll be determinant of A transpose on the left equals determinant. I'm going to rewrite that scalar as a -1 times A because it reminds us of a property we can use right here. Well, the size of the matrix is n by n. So that means on the right-hand side, you can take this scalar -1, factor it out, but you just have to ensure you raise it to the power of n, the number of rows in the matrix A. So that handles the -1 there. You multiply the rest by determinant of A. And now the right-hand side is handled. We need to do something with the left-hand side. Anyone see what this would turn into? Exactly. You could just drop the whole transpose symbol and get determinant of A. So we now have that the determinant of A is equal to whatever this is times the determinant of A. This is where it gets a little bit foggy, I think. But one excellent problem-solving strategy is that a math problem that's written well will only give you the information you need. And if you didn't use some of the information, then there's probably a mistake, or it was a poorly written question. Anyone see any information in here that we have not yet used? Everything but this, rather. That's the conclusion. We're trying to arrive at that statement.
I think that it's mentioned that n is odd. I think that might be
Exactly.
useful.
Absolutely. We've never used this. And kind of makes sense. I mean, I wouldn't have any clue what to do with that at the start of the problem right here. It's not clear how it enters into the problem, except when you're looking right there. If n is odd, that's an automatic -1. Let's write this here in the margin. Since n is odd, -1 to power n, even though we don't know the size of the matrix, it's just -1. So we have a glorified -1 on the right-hand side. We can write this as negative determinant of A equals the determinant of A. Now there's exactly one solution to an equation like this. The determinant of A is just forced to be 0 right at this stage. You could take an extra algebraic step and say add determinant of A to both sides, but you'd be left with twice determinant of A equals 0, and same exact conclusion as on this line right here. This implies immediately that the determinant of A is 0. That's the zero product property. It works here, but not for matrices. This is a real number, so it actually works in this situation. Well, we just showed that the determinant of A is 0. What are we wanting to show? This right here. So we can now just make a really fast conclusion. Because of this, this shows A inverse does not exist. So if A inverse does not exist, let's jump to characterizations of invertible matrices and go to that statement. By part E, the columns are linearly dependent. Every statement here for that matrix A is now automatically false. Again, pretty curious because that was not a lot of information to arrive at this. I already forgot what part that was. Part E. Let's say by part E of the invertible matrix theorem, the columns of A are linearly dependent. Well, we did it, folks. That's properties of the determinant so far. Any questions at all getting through this one here? Okay, I'd say that this example does not make a very good exam question, but it's great for studying for the exam because of these parts right here. The whole purpose of example 5 is just to look at properties of determinants again, and then coming back down here using the invertible matrix theorem. But I would say this one is a little bit out of reach for a real exam question. Since it's a 20-question exam, they can't be any one question this long. But let's save this up. We're now ready for section 3.3 on Cramer's rule. Any last questions or comments at all with this section? Okay, so here's our last section we'll take a look at in chapter 3. We're running through that pretty quickly. That means next chapter will be in section 4.1 for next class meeting. I did have the early draft here that was posted, but I deleted it since I'll be modifying that over the weekend. I'm posting it a little bit early. So if you want to start early studying it, it'll be available. But now we're inside Cramer's rule. This section is going to be kind of a short section for us. We're only going to go up to page 188 on the end of example 2. There's loads of other really great stuff in there if you want to do the optional reading beyond that section or beyond that example 2. But here's how it goes for Cramer's rule. This one is always kind of a confusing rule to give. Let me show you what it gives us first. Cramer's rule is a method that takes a matrix equation like this and systematically produces the solution giving component by component, x1, x2 through xn, in this particular way. It's not exactly efficient, but it's used in certain situations. Down below, you're modeling a system and you have a parameter that you're interested in, Cramer's rule is a great use right here. We can see what happens to the solutions as the parameter changes. But in all honesty, Cramer's rule is used a lot in differential equations to derive certain methods. It's used quite a bit in engineering, and so that's the main reason we're covering it today. Starts off with this. We're looking at notation matters first to begin with. We are only dealing with square matrices with Cramer's rule. So we have a square matrix A, pick any vector B in Rn, and this object. Let's zoom in on that a bit. It says AIB is going to be a brand new matrix. It's obtained from the original one, and all you do is you go to the ith column, here it is indicated, and you just insert the vector B. So we denote that as AIB, another weird notation for matrices. So this is our matrix right here, and X is X1, X2, B equals 9, 8. We're very interested in those matrix equations. And to work Cramer's rule, you just have to say what is A1B and what is A2B. So this example is nothing too major, just getting used to the notation. A1B goes like this. We go to the original matrix A. Because of the 1 right there, it means that column is inserted into column 1 as 9, 8. The rest of the matrix goes 5, 0. And so that's our formulation for A1B. Does that make sense to folks on how we got that matrix? Okay, likewise, it's not terrible notation. We just have to be familiar with it if we're going to use it. A2B goes, first carry in the original column, 1 of A, -1, 14. And because it's specified as subscript of 2, we'll take this vector B and throw it into the second column for a 9, 8. And we did it, folks. If we can get through those two, then we're well on our way for Cramer's rule. Any questions at all about them? Okay, so that's the major ingredients for the notation of Cramer's rule. Actually using it is not terrible if you have a system of this size. If you have 2 equations and 2 unknowns, Cramer's rule is, it'll take probably longer than row reduction, but it's not super terrible to get through. We'll also practice this way for a 3x3. This is more just for extra practice with Cramer's rule and taking determinants. But here's what it says. If you have a matrix equation in this way, then take the determinant of AIB for your numerator, divide by the determinant of A, and this will generate xi for 1, 2, all the way to n. But that means the very first thing you need to do in Cramer's rule is you need to take your system of equations and transfer it into a matrix equation. That was a problem right on exam 1 as well, so it's another one of those familiar topics. You can take this and begin by putting in 1, 3 to correspond for x1, 2, -1 to correspond to x2, x1, x2 equals 3, 1. So now we have a matrix equation like above here. It's not a bad idea to sometimes label what we've got. So you can think of this as an A, X equals B. This is kind of lazy convention for labeling, but I'm thinking B as being 3, 1, A as being that matrix there, rather than writing A equals, B equals, and so on. Next thing you'd want to do is, let's actually put down some steps on this. I think it would make sense for this process. Step 1 is to write out the matrix equation. And in step 2, I would take the determinant of A itself. It's going to form all your denominators, so we might as well just clear that one up. Determinant A. Let me use a little bit of color coding so we can see the process slightly better. Determinant of A means we're taking the determinant of this stuff. So 1, 3, 2, -1. And we've done quite a few of these now. This turns into -1, -6 for an overall determinant of -7. So now we have all the denominators. Well, there's going to be 2 denominators. Now we're gonna you could do this in a different style of crank out the numerators. But for this kind of system, I'd probably just go right down to step 3 and start solving for x1, x2 right at this stage. So x1 says you have to take the determinant of a1b to start. So here's determinant a1b. The denominator will be determinant of a. So now for numerator, when it says a1b, we'll take this right here, 3, 1, and throw it into column 1 of the matrix A. Column 2 is this one, 2, negative 1. And we pre-calculated the denominator. It's just a glorified negative 7. Let's pause right here. This is finally Cramer's rule all coming together, getting that numerator in. Does that make sense to everyone on that determinant? Awesome, glad to hear that. If you're happy with where we're at right now, then good news, we have half the solution. We just need to crank out this determinant. It is a negative 3 minus 2 divided by negative 7. So this will turn into a 5/7 altogether. So I'd be doing x1, and still in the same step, doing x2 is just as fast. The only thing we're changing is that subscript right there. It'll turn to an a2b. Divide by determinant of a. And so now, like before, negative 7 down in the denominator. For a2b, that implies insert into column 2 right here, the vector b, 3, 1. And then just use the original column 1 for matrix A. It was 1, 3. And you know, Cramer's rule is not too bad if you're doing a 2x2 system. It's just a couple relaxing determinants like these. Numerator is going to be 1 minus 9, all of which is divided by negative 7. So we'll get negative 8 divided by negative 7 for 8/7. That means we did it, folks. For this system of equations right here, we have fully specified the solution set. X1 has to be 5/7, X2 has to be 8/7. But we absolutely know that solution is unique because the determinant here is non-zero. This entire matrix right here would never have a free variable. Every column is now a pivot column. Any questions at all, folks, on running through Cramer's rule for this one?
I had a question. So I just wanted to make sure. So in order to find A1B, we just replace column 1 by B.
Exactly, yes. This whole column just gets swapped in with that column there. Absolutely.
Is it the same? Is it only for a 2x2 matrices, or does it work for like pretty much all matrices?
It'll be pretty much all matrices as long as your matrix A is square. Absolutely. And we're going to try it out to 3x3 down below just to see how it goes in that setting as well.
Okay, thank you.
You bet. Other questions about it? Okay, well, let's try out that 3x3 next and see how it goes. There's one in the homework, so I felt bad not doing one in class. That would just not be fair, I'd say. So here's our version of a 3x3. I think the one in the homework has more zeros inside right here, so it's a little bit nicer to get through. This would be kind of a worst case scenario. On a real exam, I'll give you one like this because we don't want to spend forever trying to get through a Cramer's rule. But word of warning on an exam, to get credit on this one, you really would have to use Cramer's rule. There wouldn't be much points for row reduction. The thrust of the problem is all about Cramer's rule for that kind of question. So I'll probably have it like highlighted, underlined, and that kind of thing for extra emphasis. But let's try this all out again. Here's our brand new system. Now you could write out the matrix equation, or you could just go right to the punchline. It is AX equals B, where A equals, let's just write these out. So column 1 goes 2, 4, negative 2. Column 2 is 1, 5, negative 1. And column 3 goes -3, 1, 4. So there's our matrix A. And if we're going to get through Cramer's rule on this kind of thing, we definitely need to calculate our determinants in a strategic way. We're going to use section 3.2 and row reduction together with cofactor expansion. Other thing we should indicate, though, is that vector right there is pretty special for Cramer's rule. V equals the right-hand side's coming from right here, so 0, 8, 2. Okay, with this setup, we're pretty much ready to go with Cramer's rule. I'll use the same color coding as before, and we need to start by finding the determinant of that matrix right there. So let's crank out determinant of A. We definitely want to do this one efficiently as possible, so let's take a look at what we've got here. Usually I try to get zeros in column 1 somewhere, but that might not always be the fastest way to go. So if you find other ways to get zeros effectively, like maybe add row 3 to row 1, and maybe 5 times row 3 added to row 2, that could work just as well. You know, honestly, I'm probably not going to overthink this one. Let's just get zeros right here. It does work. So carry in 2, 1, -3. Multiply row 1 by -2, add to row 2 will give us a 0, 3, and a 7. Let me double check. That was multiplying by -2. So -4, -2, 6. Yeah, that looks like a 7. Now just add row 1 to row 3 to get 0, 0, 1. And that's nice. Anyone able to state the determinant just by inspecting it at that stage? Exactly. We'll just take the product of the main diagonal this way, because this one is upper triangular. That definitely deserves an exclamation mark in the context of calculating a determinant, since it's going to be the product of the main diagonal going this way. So all of our denominators are now 6. That's kind of nice. We now just need to crank out x1, x2, x3 using AIB and that whole process in Cramer's rule. So here's where it gets a little bit more involved, I'd say. For this next process, it might not be as wise to do it this way because my determinants in the numerators are now involved potentially. You wouldn't want to take a whole bunch of steps with denominators you're carrying around. So what I'm going to do is now calculate all of the numerators next, A1b, A2b, A3b, and their determinants. But it's all up to you how you'd like to break up the process. I'll go determinant A1b and just pre-calculate all of these things. Because this one is A1, we're going to take this vector B and place it where column 1 would have been, so 0, 8, 2. The rest of the matrix A is identical, so let's copy in 1, 5, -1 going column-wise, and -3, 1, 4. Now looking at this, let's see, how can we get some fast zeros? You could just say multiply row 3 by 4, add it to row 2. That would eliminate the 8 right here. Let's see if that will work out for us. So 2, -1, 4. Multiplying by -4, adding above is going to give us a 0. This will be 9 next. And -16 plus 1 for a -15. We already had a 0 here, so this is looking kind of nice. 0, 1, -3. And the sign chart will go positive, negative, positive. So we'll start with a +2. In this cofactor expansion, we're eliminating this way and leaving behind 1, 9. -3, -15. And this one keeps on going, but we're just about there. We'll have 2 times -15 minus -27. These numbers are not getting super friendly. Let's see. It's 27 minus 15 takes us down to 12 by 2. I'm thinking 24. That look all right to folks so far? Okay. 2 more to go. We're getting through it. That's the rough thing about Cramer's rule is it is a process sometimes. It's not usually used to just simply solve a system. It's used in other contexts. So all we're doing here is purely just practicing how Cramer's rule would go. Well, let's try it again. Determinant A2B, sensing the need to scroll a whole bunch. So let's carry this down. And here's how it's going to run. Determinant A2 of B says we're pretty much just doing this. The 2 right here is signifying that the vector B is going into the second column as 0, 8, 2. And then the rest of this matrix A down below is copied in directly. So 2, 4, -2, -3, 1, 4. Any questions at the moment, folks, to this stage? Okay, now kind of the nice thing about Cramer's rule is if you had a 0 right here, you might notice the same strategy that I used to calculate this one is also going to work here, just the same. You can multiply row 3 by -4, add it to row 2, and you have your 2 zeros for a fast cofactor expansion. You'll also be on the lookout for maybe a way to do it even quicker if you see one. I'm not too sure I do, so I'm just going to go with that same basic strategy. So row 3 is -2, 2, 4. We're multiplying it by -4, adding it below, so that's going to be 8 plus 4 for a 12. This will be -8 plus 8 for a 0, -16 plus 1 for a -15, and then 2, 0, -3. Might be a good idea to be more careful on this one. The sign chart is going to go positive, negative, positive. That takes us down this way. And then here will be negative that we use for the sign on that too. We'll do a cofactor expansion going down that column. So next step, this turns into a -2 multiplied by, let's see, we're eliminating column 2, row 3. So it's 212, -3, -15. These numbers are killing me, but we'll get through it. We'll pull out a calculator if we have to. So now it's -2 by -30 going this way, minus a -36 going this way. These are not too bad. That's a positive 36 minus 30, so we get a 6 by -2. I think we're looking at -12 on that one. One last one to go, folks. Any questions so far? I'm going to highlight these just so we can grab them easily when we go to the last stage of this. Last thing we need is determinant A3B. I need to learn to write a little bit smaller in these kinds of things, I'm thinking. So determinant A3B. First, let's just carry in columns 1, column 2 from the matrix A. 2, 4, -2. 1, 5, -1. Then insert that column vector B into the third position, 0, 8, 2. Now we could solve this exactly like we did before, but I'm noticing when I'm multiplying by 4, my numbers are growing a lot. Or you could just take row 3, add to row 1, and you produce a 0 right here much more cleanly. So this is a good one to try to find always the fastest way possible to do this. It turns into some kind of weird numerical game. So copy in row 3 just as it is. 2, -1, 2. Same for row 2, 4, 5, 8. Then we're taking row 3, adding it to row 1 to get 0, 0, 2. That's not too bad. The sign chart is going to go positive, negative, positive. So we'll use a +2. We will eliminate, because we're doing a cofactor expansion this way, row 1, column 3. And so it's a 4, 5, -2, -1. Almost done, folks. So this turns into a 2 times -4 minus a -10. So that's 10 minus 4 for a 6 by 2. gives us a positive 12 altogether. And that definitely is a lot of work, but think of it as really good practice on doing 3x3 size determinants. We did 4 of them to work through this. Any questions at all, folks, to this stage? Okay, the hard step at the moment is to try to find the right level to zoom out in to find everything we need. So the denominator is always going to be 6. Let's copy that down. And now we can start writing out all of our solutions. Like on the last problem, I'm just going to specify them as a x1 equals, x2 equals, and so on. So x1 is going to be equal to, put the 6 down below, and if it says x sub 1, we go to determinant a1b to find our result. 24 will be the numerator for that one. So 24 goes in. I'll highlight this in yellow just to show where we got it from. And that shows x1 is 4. Then just rinse and repeat. We did all the hard work. We're just summarizing. Next one is x2 for a denominator of 6. And look up a 2b. The numerator is now negative 12. So this comes out as a negative 2. And last step. x3 also divide by negative 6. Excuse me, positive 6. We'll have a numerator of positive 12 right here. Forgot to carry those highlightings in. And so with all this work, we found x3 is 2. We did it, folks. There's a way to solve this system that's actually worse than row reduction. It's kind of hard. But if you're studying Cramer's rule, then that's the purpose of this one. You usually would not use Cramer's rule just to solve the system. Any other questions at all, folks, on getting through it?
Would there ever be a situation where you would replace a row with B rather than a column? It's a different rule, but
Yeah, I would have to think about that. If you're replacing a row, that would say you're doing a transpose of this right here, but that would mean you're transposing the coefficients here. I'd have to think about that. Let me put down a quick note. Rows in Cramer's rule. I think that's a really good thought, and you could be surprised with this kind of stuff. There might actually be a process for that, but as far as I know, I'm not too familiar with what it would be. But other questions about that so far? Okay, I'm going to take a look at this. That's actually a pretty curious question, and I'll report back. This will be my homework over the weekend if I found anything in that direction. When we come back from the break, we're still going to finish off this example 4. And down below, this is now optional reading. If you wanted a formula for inverting a 3x3 matrix, here's the theorem, but it's another one of those things like Cramer's rule. That's probably not the most effective way to calculate by hand. It's more of a theoretical result used in other niche areas. But we'll call it a day today and come back here on Tuesday for example 4. Have a great night, folks, and I'll see you all next week.
Thank you so much.
You betcha. Have a good one.
thank you.
Thank you. Yep, have a good one.